Hello, good morning, good afternoon, good evening, everybody, wherever it might be. Today is my great pleasure to introduce my former student, MARIUSZ Tobolski. He graduated summa cum laude from INPAN, and today he will take us beyond the compact case with compact principal bundles, quantum principal bundles. The floor is yours, take it away.
Thank you very much. So, okay. Can you hear me okay?
Yes.
Yes.
Great. So yes, I'll talk about quantum principal bundles beyond the compact case. And what do I mean by this? So first of all, so I had some technical difficulties with stuff. That's why it's so chaotic at the beginning. First of all, it's very nice to talk at this North Atlantic Non-Commutative Geometry seminar. So it's nice to give a talk here, even if it's not in person, but online. And now the title, Quantum Principal Bundles Beyond the Compact Case. And well, this implies that there is the compact case, right? And it's been for quite a while, a lot of work on generalizing principal bundles to the non-commutative geometry. And I'll talk about this. And I would like to go beyond the compact case, it said, because it's not that much done in this setting where the bundle is no longer compact, but by which I mean that both the group and the space are locally compact, because we still want to be in the framework of non-commutative geometry. So let's start with the plan of the talk. So first I would like to tell you, because this will be like a really non-commutative geometry or non-commutative topology talk, where I have something classical, I want to generalize it. And so first I would like to tell you what I want to generalize, right? And there will be this battle between Stenoth principal bundle, Cartan principal bundle, that was in the 50s. I'll tell you who won, and I'll also tell you what was done in the efforts to generalize this notion. So I'll talk about the good old days, as I wrote here, some history of compact quantum principal bundles. And I think it's maybe worthwhile because there are surely a lot of experts in the audience on compact quantum principal bundles, but I think it's still nice to give some history. And then for people that are interested in the topic, I'll have lots and lots of references. So if you get hooked up to this and you'll be interested, then you can look it up. Then I'll go to infinity and beyond. So maybe, to compactness and beyond. And I'll talk about trivial bundles, because if you want to have locally trivial bundles, you first have to talk about triviality. And then I'll talk the notion that together with Eusebio Gardella, Piotr M. Hayat, and Jinchao Wu introduced in the case of, in the compact case, but I'll tell you what I mean by this in a second. And then, beyond the compact case. And in the end, as the famous baseball coach Yogi Berra says, it ain't over till it's over. So there will be some outlook in future work.
Sorry, Mariusz, I'm still seeing the first slide.
Yes. So that's okay.
Okay.
Yeah, so that was a long introduction. That's what you meant.
Yes.
Okay, I'll try to wrap it up a bit. Okay, so that's the plan of the talk. So you have a roadmap in your head, and now let's start. So there were two competing, so I want to talk about principal bundles. So I'll give you the definition of a principal bundle, but I'll actually give you two definitions, because there were two competing definitions in the 50s. So in this talk, so G will always denote a topological group, and X will always be a topological right G space. So I have this convention of having right actions. This is a convention that is usually used in the theory of principal bundles.
By the way, Mariusz, I understand why Adam is worried, because you see, you have 95 slides and you took 4 minutes for one slide. So 4 times 95, that's quite a long seminar.
Okay, but probably if I click now, the counter should change, right?
Yes.
Okay, so that's good. So I think I have like 25 slides. There I have a lot of those pauses that.
No, I'm still seeing the first one. So
yes,
I know.
Because that's what he's showing.
Oh, you're still seeing the first slide?
Yeah, now we still see the first, yes.
You don't see this.
I cannot even see the first slide in full because
yes, exactly.
This frame of Adobe Reader instead of taking the full screen.
I confirm, yes.
Okay, so let me maybe stop sharing and try to do this again. Oh, okay. Well, so that's a bummer.
Something got frozen. Yes, it's much better now. Yes.
Much better. Okay. So, but I would like to go back. Oh, so I was talking to you about all those. Okay, now you see this slide, plan of the talk?
Plan of the talk, yes.
Okay, so in the plan of the talk, I had this all written here. So I was actually reading. It was not that I had all those good jokes from the top of my head, the good old days, the infinity and beyond, and it ain't over till it's over. So that's the roadmap. Okay. Now you can see the definitions. Great. So G is a topological group. X is a topological right G space. So now a principal bundle in the sense of Stenoth. So that's something you will find in the book of Stenoth on topology of fiber bundles. I think it's 51. It's 1951. We say that this bundle, and by principal bundles, I always mean bundles of this form. So you can think of some other space here, like X over some other space M. But for me, it all comes down to bundles of this form. And also, if you talk about non-commutative geometry, it's much easier to just think of bundles of this form. Okay, so that's one comment. And then this bundle, X over X mod G, is a Stenoth principal bundle if, and I have this one condition, which is the local triviality condition. So if I find any point in the base space, there exists a neighborhood of this point such that I have, a neighborhood and a homeomorphism, a fiber preserving G homeomorphism from pre-image of U to U times G, where here the action is trivial on U, and this is action by multiplication on G. Okay, so that's the definition of Stenoth. This is a locally trivial principal bundle. And then we have the second definition by Henri Cartan that we say that this bundle is a Cartan principal bundle if, first of all, we want to have free action, so Gx freely on X, and then we have this condition. So this tau map is called the translation map, and it goes from this fiber product to G, and the definition is as follows, that tau of xy equals to G if and only if X times G equals Y. And you can see that this is well defined because the action is free, so this G is unique. Okay, so if you have a free action, then you can define this translation map. This map might not be continuous in general. So we ask it to be continuous, and then we talk about Cartan principal G bundles. So,
excuse me, Mariusz, may I ask a question? Yep. Maybe I missed it.
Yep.
What are you assuming about X? Just that it's a topological space? No.
Yeah, for now, I'm just assuming that this is these are two topological spaces. I'll quickly talk about locally compact spaces in a second, but for now, this is just some general topological.
Okay, thank you.
Yeah, considerations.
And I'm sorry, Mariusz, because it's something that I point to over and over again. I mean, in Cartan's definition of principal bundle, there's one more condition that this X cross X over X mod G is closed in X cross X. It's called Cartan's FP1 and FP2 conditions, because here you can still something that Cartan would call more like, you know, a foliation. I mean, if you take Reb's foliation, then it will be a principal bundle according to this definition.
Yeah, sure.
Because the action will be continuous, but the image will not be closed. So the quotient space here will still be very ugly.
Yeah, thank you. So Alex is asking about this fiber product. Exactly, yes. So what this X over X mod G two points x and y belong to the same orbit. That's what it says.
Yeah, exactly. Yes. Mm-hmm.
And yes, we have. Thank you for this question, Piotr. It's we talk about this over and over again. Yes. I always have this citation to Palais paper. So this is what I'm citing. This is not my idea, but if you go to original Cartan's paper, the definition is a bit different, right? There's this second condition that is assumed, which is not present here, and this condition is has to do with properness of the action more than local triviality, and that's why I don't want to assume it here, and it will be not needed in what follows.
Alex has a question.
One comment is also, yep. Yes, I already answered.
No, Alex raised hand, so.
Oh, I raised hand. I cannot see that. Okay, thanks.
Yeah, sorry.
Yeah, hi, Alex.
Hi, sorry. So I just want to know, like, can you give like the idea, like, behind these different notions of? So first of all, what would be the idea of something being a principal bundle, and what is the idea behind Stenoth and Cartan, like in words, like maybe something.
Yeah, like sure. Okay. So first of all, if you look at principal bundle in the sense of Stenoth, right, then you have this local triviality, which means that you have something which locally looks like a product, right?
Yes.
So you have something that looks like a product, and then you have this action, and now you can
second
prove
one. Sorry,
the sure. You can prove that this definition of Stenoth implies this one. Okay, so this condition of local triviality, you can prove that the action is automatically free if you have this local triviality, because freeness is local. So this can work. And then you can also prove that this map will be continuous from this. So it's always one way. So Stenoth implies Cartan, and then there is an example. You can find an example of a Cartan principal bundle that is not a principal bundle in the sense of Stenoth. So first of all, you have to look for groups that are not Lie groups. Because for Lie groups, this will be the same. There's a theorem by Gleason that all free actions of compact, let's say compact Lie groups, give rise to Stenoth principal bundles. So if you find some group that's not a Lie group, let's say that looks like a Cantor set, take an infinite product of Z2 and act on infinite product of circles, this will be still a free action. So it will be a bundle in the sense of Cartan, but not Stenoth. So that you don't have this local triviality. So you have a free action. Yes. Everything is quite nice. This continuity of this translation map that I also wanted to point this out. In the case when everything is compact, this is automatic. Okay, so if you look at compact principal bundles, in the sense of a Cartan, these are just free actions. And this is basically what I want to say, is that that's the main message of this first slide, that in the compact case, Cartan principal bundles, these are just free actions of compact groups on compact spaces. So this is very simple. And this is what people generalized, right? Because freeness is much easier to generalize than this local triviality condition, because here we have open sets and we don't know how to define an open set in this non-commutative setting or an open cover. So this took a while. There was some mental block here, but yeah, I hope I answered your question.
So can you tell the idea behind Cartan's definition? Like what is the second requirement, like that this is continuous? Like
so you just look at this. So I remember that I had some very intuitive.
May I answer this question?
Sure. Yeah.
You see, it's good to understand it if you take a counterexample. So for instance, if you take the Kroneker's foliation on the torus, you'll have a nice free action, okay? Continuous free action, but this will be discontinuous, right? So that's the idea is, so that's why you really must have it, right? And as MARIUSZ pointed, this is implied by the Stenoth definition. So if you are locally trivial, then indeed this map is continuous. However, now I understand why you skip this second condition of Cartan, because the second condition of Cartan is not implied by Stenoth. And again, the Reb foliation is precisely an example. because over there you have everything is locally trivial. You have local sections, you have local triviality, but the action is not proper. And therefore the second Cartan condition of this subset, this fiber product being closed in the full Cartesian product is not satisfied. Okay, and this is very easy exercise to realize it. So the only so it makes mathematically perfect sense. It's the fault of Palais, not Mariusz, that he called it Cartan. He might have called it semi-Cartan because he took away a very important condition from Cartan's definition, which indeed then is equivalent to demanding that the action is free and proper. And Mariusz is right, when you are compact, free and proper means just free. But basic distinction, Alex, is that one has local triviality, the other one doesn't. And as Mariusz pointed, when you go beyond Lie groups, local triviality is not given for free. We have many extremely important natural examples where principal bundles are not locally trivial, but then your group is something like totally disconnected, like Cartan, not Cartan, Cantor set.
So the example that you mean, is it like that, like the how to say this wrapping around the torus, like that has dense orbit? Okay, yeah, I can see.
Yeah. Then this translation map is not continuous. So that's like a minimal thing that you want is at least let this translation map be continuous.
Yeah, got it. Thanks.
Okay, thank you, Piotr. So my connection is a bit unstable. I hope you can still.
You mean it's not a strong connection?
Yeah, it's not a strong connection. Well, about strong connections, I have my next slide. Right, it's here, like strong connections here, just in time. Okay, so let me talk. I just want to talk a little bit about history of compact quantum principal bundles, and there are basically two approaches that one can. There are two approaches to this generalization of geometry. One is purely algebraic. So the role of your group is played by a Hopf algebra, and the role of your space is played by H commodule algebra, if your Hopf algebra was H. Okay, so and then there's this theory, and this is probably not the first paper where it was introduced, but it's a famous paper on Hopf algebras and Galois extensions. So in this paper, the work of Galois was extended using Hopf algebras, and this is a purely algebraic setup. And then in next papers, it was people realized that this is really connected to principal bundles, and that this generalizes the notion of a Cartan principal bundle. Okay, and it was then developed by Brzeziński and Majid, where they talked about gauge theory on quantum spaces, and then Djurdjevic had at least 3 papers on quantum principal bundles. And then strong connections, and the paper by Piotr, when he married this theory of compact quantum principal bundles with K theory. So these were the good old days, right? The 90s. And the next few references that I have here are just showing that this is still a topic that is of interest to people. So there are plenty of papers still. Some two papers in 2005, one on the homotopy equivalence by Castle, and then by Landi and Van Sulekom on principal vibration from non-commutative spheres, where they study examples like SU2 actions on theta deformed spheres, where you have to adjust theta a bit to have a coaction. And then there are those two recent papers just to show that this is still a lively topic. Okay, and that's this algebraic approach. I just wanted to show you some references. Instead, it's never too late, right, to hop in and work on compact quantum principal bundles. So that was the algebraic approach. And then the sister algebraic approach, people were also talking about this. And here the message is, of course, that I'm talking about the compact case. So I want to generalize compact Cartan principal bundles. I have the only, here in this definition, this point about this translation map, this is automatic. So I only generalize 3 actions of compact groups and compact spaces, right? And here there are a few papers with freeness, like this book by Christopher Phillips here, and this paper on free actions of finite groups. And there's this paper by Mark Riefel on proper actions of groups. And he also talks here about generalization of freeness. It's called, he calls it saturatedness. So we also have this paper I found just rather recently. That was actually a first approach to generalize principal bundles, and even locally trivial ones. But in the context where you actually think of not the C-star algebras themselves, but so you look at an action of a group on the C-star algebra, but then you want to have a principal bundle on the primitive ideal space. Okay, so this is like semi-classical, I would say, because all the non-triviality is really in some classical core of your bundle. Okay, so a few papers left. So there's this paper by David Elwood where he talks about freeness and properness even. So here he's really general. So he talks about locally compact quantum group actions on C-star algebras, and he gives this definition. And why I'm showing you this slide and the C-star algebraic approach is that it turns out that the approach of Elwood, first of all, is equivalent for in the compact case to the definition of Riefel, and that was shown by the Kommer and Yamashita. And then, better still, Baum, the Kommer and Hyatt showed that this approach, well, this definition of Elwood is equivalent to the algebraic approach. So there's actually just one approach in the end, right? So this is all equivalent. There's this functor that you can apply from one side to the other. And it goes like this, because here in this paper, they have compact quantum group actions. So for a compact quantum group, you have this dense Hopf subalgebra, and then you can also find a dense subalgebra, a dense comodular algebra of your C-star algebra, unital C-star algebra, okay? So this is just to show you that this is, there's already a lot has been done to generalize principal bundles in geometry, but all of these works, they were dealing with generalization of Cartan principal bundles.
Mariusz,
right?
Can I ask?
Yep.
It's Ludwig Hajta. So the one direction, I mean, you forget about topology probably and go to algebraic stuff, but
yes,
every algebraic bundle in this sense with free action can be C-star algebraized.
There is some kind of an enveloping algebra. That's what Kennedy Kommer proved, that you can go to completion. Yeah, you can complete it.
Yeah, but not always. I mean, it's everything which is in the C-star case can be mapped into principal comodular algebras, but not every principal comodular algebra can be completed to a compact.
Yeah, sure.
Yeah. It's exactly like what Voronowicz did. We have Peter Weil-Hopf algebra, and it assigns to the C-star algebra of a compact. I mean, it assigns to a compact quantum group in a natural manner a Hopf algebra. So that's precisely the same thing which we do, but instead to a compact quantum group, we do it to a compact quantum principal bundle, and we obtain instead of a Hopf algebra, we obtain a comodular algebra over Voronowicz Hopf algebra.
Yeah, exactly. That's what I meant.
For instance, Hopf algebra must be cosemi-simple. If it's not, forget it. It's more general. Yeah.
Yeah, of course. That's what I meant. I meant that if you have just for this Peter Weil algebra, so you have to have your you're right. Also, the Hopf algebra has to be this Hopf algebra that you can have a compact quantum group out of it. So then semi-simplicity is yeah, okay.
At least, okay.
Yeah, sure. So it has to be a CQG algebra. Sometimes that's how people phrase this. Okay, any other questions? Because surely I forgot about some names and stuff. So any comments from the experts are welcome. Okay, so let me go here. So I want to talk about this Stenoth approach, and let me tell you why, because also this, I told you that there was a battle and I didn't tell you who won. So of course Stenoth won in the sense that in most textbooks, under the name principal bundle, you will find the definition of CNOT. This local triviality condition is implied. It's also because of the applications, because if you have local triviality, then you can do gauge theory in physics, you have some coordinates and stuff like that. So that's why principal bundles in the sense of CNOT are much more popular.
It's just like Lie groups are more popular than some p-adic groups, you know.
Well, yeah, sure. I'm not saying that something is better or not. But
no, of course, no. It's just popularities.
But there's this. So, but also, if you have Stenoth principal bundle, you have this whole classification machinery. You have universal spaces, so which were defined by Milner. So there's a lot of additional things because you assume more, so you get more. Right. So that's how it is. And there was some work on to find this in this algebraic setting. And I'm only listing here the work of Markus Pflaum, who was using sheaves and more of an algebraic geometry approach to local triviality. And in the end, what it turns out is that he was generalizing a different notion, which I call here piecewise triviality. And this means just that instead of open covers, you look at finite closed covers, which trivialize your bundle. Okay, and these two are even classically different. So there is an example of a piecewise trivial bundle that is not locally trivial, which was cooked up by Paul Baum, and it's called the bubble space. I don't have, unfortunately, here the reference to this, but if you ask me, I can just give you the reference. Then in the C-star algebraic context, that's something that I already talked about, this local triviality dimension. We believe that this is the right notion, and it really recovers the classical definition of a local triviality in the compact case. And this is basically, this part is what I want to talk about and what I want to generalize. Okay, and just for sake of completeness, in non-commutative algebraic geometry, there is also local triviality. So if you look at this paper, quantum principal bundles on projective basis, there will be local triviality there stated. However, it's different, right? Because this is algebraic geometry, not topology. So this is generalizing a notion of local triviality in algebraic geometry. And here we talk about topology. So things here will be Hausdorff.
You're absolutely right, Mariusz. Here, this paper of Vaschieri and Fioresi Latini, this is precisely this algebraic geometry approach, where you localize by inverting some elements in your algebra. But for Pflaum, I wouldn't say that it had anything to do with algebraic geometry. Just because he used the lingo of sheaves doesn't mean anything. This was really, as you put, piecewise triviality in the algebraic context, but not algebraic geometry context. That's algebraic geometry. Yeah.
Okay, thank you. So yeah, so that's that, and that's the end of history. So yeah, so now I can start my talk.
Yes.
And the aim of the talk is, as you already probably noticed, is that I want to generalize the Stenoth principal bundle, but I'm just going step by step. So my setting is of locally compact group actions on C-star algebras. Okay, so my algebra may have a unit or not, and the group is locally compact. And by locally compact, I mean Hausdorff. So in my slides in this talk, there will be no Hausdorff spelled out, but I always assume it. Okay, so that's the disclaimer. So whenever you see locally compact, yep.
Just a stupid question. You said that your algebra may or may not have a unit.
Yes.
Well, if it has a unit, then it's like a compact space. So when you have a non-compact, okay, because when your group acting freely will also be compact, right?
Yes. So that's true. So this. Because freeness, like somehow you have to embed your group, right?
Exactly. This is why I had some red flags.
Yeah, that's true. Yeah, that's true. So then the group will be compact, of course. But I just want to be as general as I can. So, and then there's this question that I believe one should ask. We should ask ourselves many times. Why should you bother? Right? I'm asking you. So what's the gain? What do you want to this generalization? Is it generalization for the sake of generalization? Or maybe compact quantum principal bundles are such a nice part of mathematics that you don't need anything more. You don't need to generalize this. So yeah, to be more precise, this theory of compact quantum principal bundles is very well developed. And sometimes, even when G is locally compact, many principal bundles can be reduced to a compact subgroup. Okay, so then it turns out that this non-triviality of the bundle is actually hidden in some compact subgroup. So you don't need the whole group, in a sense. So in principle, there's, well, maybe there's not much to do. However, there are still non-reducible principal G bundles for any group G. Right? You can take, let's say, topological join of G with itself, right? And this will give you a bundle that over its orbit space, because you have the diagonal action of G when G is locally compact. Then you have continuous diagonal action, and this will give you a bundle that is not only non-trivial, but also non-reducible, right? So that's why this is not just generalization for the sake of generalization. Compact principal bundle do not cover even in the classical case or all interesting examples. And then, okay, well, generalization for the sake of generalization is not that bad, at least for me. So it would be nice to have a general theory of locally compact quantum principal bundles in the sense of Stenoth. Right? Okay. And if you want to talk about local triviality, you should start with triviality. So this will be talk about triviality. That's why this is trivial. Okay.
Sorry, Mariusz, I have again a stupid question. Yep. I'm not sure, but I think it's not sufficient just to take a join of a locally compact group and say, aha, so then it's not reducible. Isn't it true that if your group, isn't it true that if group is contractible, say like real numbers, if you take the join of real numbers and view it as by the diagonal action as an R principal bundle, then I think it's trivial, is it not? Yes, it is. Because triviality of a join of G with G is tantamount to this being homotopic to a point. Yeah, so that's actually subtle. It's really a very subtle point to make sure that you get a non-compact group, locally compact group acting on the space freely and nicely. But then you want to make sure that this non-compact bundle cannot be reduced to some compact core that is no longer reducible. Yeah. Because this was a nightmare when doing compact quantum principal bundles ages ago. That what's the point of having all this quantum setting if the whole non-triviality is in the classical subgroup? There were such results. So you basically decorate classical principal bundle by trivially extending fibers to quantum spaces. That's not very interesting, right? So here we have a similar problem. We want really to have genuinely non-compact bundles. We want to have non-compact bundles that cannot be reduced to compact subbundles. Yeah, exactly. So that was the point, but I missed this that maybe the group should not be contractible, like take integers, for example, right? Yeah. Then you would have, and integers is a very nice group, right? Yeah. So that would be a lot of examples that are still yet to be in this framework of locally trivial principal bundles. And okay, so that was the motivations. And now let me start with triviality. So if you have a locally compact space and a locally compact group acting on it, we say that the principal bundle is trivial if it just looks as a product. It's not locally a product, it is a product. So X is homeomorphic to X mod G times X as G spaces, where here the action is trivial on this part and it's by multiplication here. Okay? And then if you do non-commutative topology, immediately you think, okay, so products for spaces, well, that means a tensor product of C-star algebras. So maybe that's the way to generalize triviality. And unfortunately, this is wrong. And let me tell you why. So for now, assume the compact case. So you have a unital C-star algebra and a compact space, okay, a compact group. And the seemingly reasonable choice would be to say that A is trivial if you have such isomorphism, which would correspond to this, where AG is the fixed point subalgebra. So it would correspond in the classical case to functions on X mod G in the compact case, right? So then the problem is that, first of all, if you want to go, so the first question is, so, okay, what happens when the bundle is no longer compact, right? Then this space can not be Hausdorff if we do not talk about proper actions.
right? So then this is a big problem. And then even if you aren't, so let's say you have some versions of this fixed point subalgebra, those generalized fixed point subalgebras that were studied by Mark Riefel, then you can still, there are still some questions to be asked. Is this the right generalization? And even in the compact case, okay, so you say, well, okay, so maybe this is the right one for the compact case. Then the problem is that it excludes many examples. So this would mean, in a sense, that you have to A, you can have a map, a G-equivalent map from C of G to A that is commuting with this A, with the fixed point subalgebra. And this is a lot to ask. So many examples does not satisfy this example. Satisfy this property. And already in the algebraic setting, people are using a different version of triviality, which is based on this classical fact that triviality is equivalent to the existence of a G-equivalent map from X to G. And this we know how to generalize, right? We have Gelfand-Naimak duality. So both spaces here are locally compact. You just reverse the arrow and you get a map. So this would be the right way to do this. So A is trivial as a GC star algebra if we have a G-equivalent non-degenerate star homomorphism from C0 of G to the multipliers. So this is the multiplier algebra of A. Okay, so that would be at least in my opinion, the correct way to view trivial bundles. And this agrees with what people are doing in this algebraic setting of compact quantum principal bundles when they talk about cleft principal bundles, right? Where this is a bit more general. Instead of a homomorphism, you have a convolution invertible map, but then triviality in this sense would imply cleftness. And as far as I know, there is some version of like analytic cleftness with C-star algebras, but I'm not really an expert on that. But there are some papers also on this. But here I only want to talk about triviality. And this is, in my opinion, the right way to do this.
You're right, Mark. The analytical version of cleftness is a tough cookie, but here we have Stefan Wagner, and I think he was working on this. That's his work, how to do cleftness in the analytical setting.
Mm-hmm. Yes. So Stefan, maybe you can say something about this.
Yeah, more than welcome to comment there too. Okay, anyway, go ahead.
Okay, so let's, if you'd like to hop in then.
Sorry, so this is this notion of the right notion of morphism in the context of non-necessary unital, yes? C-star algebra, yes. This was due to Voronovich, yes?
Yes. Okay. You can try, of course, different ones, and I will give you a different notion of morphism just in a second when you want to, well, you'll see. Okay, but this is the version, like generalized version of Gelfand-Naimak duality due to Voronovich. This non-degenerate star homomorphism. Non-degenerate here means, right, that the image of that times A is dense in A. Right? So that's what's this non-degenerate about. Okay, thank you. Any more questions about this? Now let's go. Example. So for any locally compact group G, you can take just the compact operators on L2 of G, where here we take the Haar measure to define this L2 of G. You take the left regular representation on this, on bounded, well, just a unitary bounded operators on this L2. So just some usual stuff. And then you define an action using this left regular representation, which is an adjunct action. So this will be an inner action of G on K, right? And here the group is locally compact. The algebra is not unital. So that's why I want to show you this example, because it's not hard to convince yourself that there is a non-degenerate G-equivalent star homomorphism from C0 of G to M of K, which is just bounded operators on this Hilbert space. And it basically goes like this, that on the compactly supported functions, you just put them into multiplication operators, right? So this is if you take f, then of course you look at its first you look at its class in L2, and then you can define a multiplication operator, and that would be basically your map, which will then extend to the whole non-degenerate G-equivalent star homomorphism. There's something to be checked here, of course, but it's rather standard. And this is an example for any locally compact group. You have this kind of a trivial bundle. Okay, so that's a nice example. And then I want to talk about local triviality now, but let me go back to the compact case for a second, because I want to tell you what was done already, what we did with this local triviality dimension. And afterwards, I would like to the actual goal is to generalize this local triviality dimension to the non-compact case. Okay, so we are going back so we're doing it just like step forward, step backwards. And now we're doing the step backwards. So, okay, unreduced cone of G. So now we have a compact group and a compact G space. And the unreduced cone is defined as follows, as the quotient. So you take a product of 0, 1 with G, and you identify at the one endpoint, at 0 endpoint, you identify the whole G to 1 with 1 point. That's your relation. And this is the unreduced cone because you have the tip. So in C-star algebras, we sometimes look at the cone as this reduced cone without the tip, right? Because then it's, as a C-star algebra, that would be just C0 of 0, 1 without 0, tensor your algebra. Okay, but here it's really important, and you cannot do this without the tip. This is really important to prove the theorem that I'm about to talk here. So we have this map, which is called the height map, which is just telling you the height where you are at your cone. Right, so to a point, to a class T point G, it assigns the point T, it assigns the element T. And now we have this theorem that this bundle is a Stenoth principal G bundle if and only if there exist G equivalent maps from X to the unreduced cone, such that this is this sum equals to 1. Right? So you compose your phi I with T, and at each point, the sum has to be equal to 1. So you can see that this is actually saying that those functions, T composed of phi I, these form a partition of unity. And that's actually what we're doing. So it's really hard to talk about open covers or open sets in non-commutative topology, but you can talk about partitions of unity subordinated to them. Okay, so that's the main idea, because those functions are in your algebra, in the compact case at least. And in this theorem, there is one subtle point, the continuity of those maps. Because to define them, you need a partition of unity. So, well, it depends, depending on from which way to which. If you want to prove that given a principal bundle, Stenoth principal bundle, you have those maps will come from, on the one hand side, those trivializing maps, and on the other, from a partition of unity that is subordinated to your trivializing cover. And then to prove that these maps are continuous, this is a subtle point, and I'll talk about it a bit more just in a second.
Sorry, I have a quick question.
Yeah, sure.
This remark about the unreduced cone. So the reduced version is, as far as I remember, a suitable version of cone for spaces with distinguished point, yes? Am I right? Where you collapse, you have on each copy of this space on which you take a cone, you have a distinguished point, and then you collapse all possible distinguished point in every copy to one distinguished point.
Oh, so maybe I meant something else. I just meant that it's a cone without the tip. That's the only thing I mean by a reduced one.
Okay, so
like that you just remove this one point. Yeah, so so maybe that's not the standard terminology, but that's what I meant.
Okay, I see. Thank you.
Okay, so now, I talked about trivial. Now I want to talk about locally trivial, and let me give you a definition. First, okay, so I just said this, that we do not generalize the notion of an open cover to non-commutative setting, but rather the partition of unity subordinated to it. Okay, so that's the main idea. And the definition is as follows. As you can see that when you look at this theorem that I just pointed out here, you just apply Gelfand-Dirac duality to it and you get our definition. You just reverse the arrows and write this down. This is what is happening, okay? You have a compact group and it acts on a unital C-star algebra, and the local triviality dimension is the minimal number of n such that there exist those maps from row 0 to row n. These are G-equivalent star homomorphisms, unital ones. Okay, so I forgot to write down unital. So these are unital G-equivalent star homomorphisms. Okay.
And the sum is from I equal to 0 up to n, yes?
Up to n. So there's some typo here. Yep, thank you. So that's this partition of unity condition or joint unitality condition. And if no such n exists, then we say that this dimension is infinite. Okay, now our definition of a locally trivial non-commutative principal bundle in this setting is that this dimension is finite. When this dimension is finite, then we talk about Stenoth non-commutative principal bundle. Okay, and then the first check would be to see if dimension 0 is actually triviality, and this actually works. So dimension 0 would mean that I have one map row like this, and said that it's unital, and row of t is equal to 1. Okay? And this, then you can prove that this is actually equivalent to having a map from C of G to A. Okay, so the fact that row of t equals to 1 helps you to write down the map not from the cone, but from G itself. Okay, so this is exactly this triviality in the sense of the previous slides, but now A is unital, so instead of the multipliers, we get A, and well, this is just a star homomorphism. And non-degenerateness is for free because it's unital. Also, I also forgot about unital here. Okay, so sorry for that. There should be unital here, and n. So that was the worst slide. Any questions? Because there were a lot.
Yeah, I don't think it's that bad, because when you have unital C-star algebras and you say star homomorphism, it's tacitly assume you mean unital.
Yes, yes. Thank you for cheering me up.
What happens if you replace star homomorphism by a CP map?
So there is a definition, because also, okay, so this definition is was inspired by the rocking dimension, right? So then in the rocking dimension, you look at CPC order 0 maps from C of G to A. Oh, not to A, to just central sequence algebra, blah, 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 right? And here, what we can do is we can look, instead of G-equivalent star homomorphisms, unital star homomorphisms like this, you could look at CPC order 0 maps from C of G to A with this joint unitality condition. That would be equivalent by this theorem by Winter and Zacharias. Yeah, but that was a good point.
Oh, you mean because you're considering the cone of G?
Yes.
Oh, okay, I see. Yes, that's very nice. Thanks.
So this is the price you pay. Either you have a homomorphism, but from the cone, I mean the C-star algebra of a cone, or you go from the C-star algebra of a group, but it's no longer homomorphic, it's some CPC or the 0 map.
Yeah,
not such a big price, right? I mean, like, you get a
well, it turns out that this cone in beyond compact case is troublesome. So you'll see in a minute. Okay. So we have this. Yep.
You stress the fact that this construction is not a generalization of an open covering, but in fact, it's about this partition of unity. But in your definition of your local triviality dimension, you refer to the notion which depends on an open covering. All dimensions in topology are defined not by means of decomposition of unity, but in terms of coverings.
Yeah, you're right. So that was just, this is, so sorry for that. That was more of a PR. You're right. Of course, it's a package. It's not that we're forgetting about it. We're doing this, that we generalize this open cover, right? But this partition of unity is more visible, but you cannot forget. So in a sense, this definition is giving you simultaneously the partition of unity and the open cover, and G-invariant one, of course, because here you have those G-covariant maps.
Or you could rephrase it by saying that we cannot give any meaningful definition of open covering beyond paracompact spaces. We can do it only using the partition of unity.
Yeah. Yeah. Okay. Thank you.
So maybe the name should be the partition of unity dimension.
Yeah. Well. Yeah. Maybe it should be like this.
No.
I'm really struggling with names. I like the names local triviality dimension, but then I'll have a notion of a locally trivial GC star algebra or a trivial GC star algebra, and it's a bit problematic. But I hope, just for the sake of this talk, and maybe at least one paper, I didn't come up with any new names. You'll see in a minute. Okay, so what's good about local? Yep.
Sorry, can you show the class of classical topological spaces when this local triviality, in the sense of this partition of unity, is equivalent to local triviality in the sense of an open cover?
Of course, all compact.
I think, yeah, all compact, but I think like if you look at numerable principal bundles, if you have a partition of unity, at least.
So numerability of principal bundles must be assumed.
Yeah.
Okay.
And so in fact, what I will be generalizing are numerable principal bundles. Okay. Or I can cop out by saying that my spaces are paracompact. So
yeah, but do you have a paracompact counterpart in the non-commutative setting?
Well, not really, right? There are some things you can prove something about when commutative C-star algebras are paracompact, and there are also some like if and only if conditions for commutative ones, but then I didn't see anyone working with this in the fully non-commutative setting. There's about existence of certain approximate units with some adjectives, but I don't want to go into this because I don't remember.
Yeah, so this name, the local triviality dimension, is too much sexy to be
no, I don't agree. I mean, when you are in the purely compact setting, it is equivalent.
No. We are not talking about the compact setting.
Oh, okay. Well, here I see the definition is in the compact setting. Tomek, the definition is in the compact setting. Let G be a compact group and A unital C-star algebra. So this is a compact setting.
Oh, so this is restricted to, yes.
Yeah.
Okay. Now I agree. Okay. In this case.
So I'll have something different, and then adjective numerable should be there somewhere. But yeah, that was a good point. Okay, let me tell you what is good about local triviality dimension, and also how am I doing with time?
Well, you still have 37 minutes.
Okay, not that bad. Okay, great. So what is good about local triviality dimension is that we have a lot of examples. I'll not go through them in detail, but you can see that there are a bunch of quantum spheres with antipodal actions, U1 actions of theta deformed spheres. This SU2 action on the theta deformed quantum sphere of Landi by Sulicom is here as well. So they prove that this is not a trivial bundle, that it's not, I think they prove that it's not cleft in this algebraic setting. And we prove that it's locally trivial. Okay, so the dimension is exactly 1 in fact. So then there are U1 actions on graph C-star algebras. So for example, on Teplitz algebra, Kunz algebras, and so on. So many examples. And this is why I think it's interesting to look at this definition, because it covers many examples. And also it implies freeness in the sense of Elwood. So of course, also in the sense of refill. So this generalizes this one fact that I wanted to, that's why my slides are such, I write down only those two things about Cartan principal bundles. So I can say that Steenrod implies Cartan. And then I have a non-commutative generalization of this fact. So yeah, now I remember why I write it down in such a way and not the other, right? So here the fineness of this dimension implies freeness. That's what is interesting. Also, we have those applications on the Born-Coulomb type conjectures, right? So actually introducing this dimension help us to prove some new special cases of this very difficult conjecture. And well, the conjecture doesn't work beyond compact because it's really like this, the essence of the conjecture is in the compact setting. So this is maybe just some PR, the wide local triviality dimension is nice, and that's not why we should look at locally trivial principal bundles, but still. And then there are those connections with the Rocking dimension they already mentioned. And so Alex asked about this, and it helped us to see that the Rocking dimension is actually more of a variation of freeness than local triviality. Because at first we thought that Rocking dimension should be some kind of a analog of local triviality in the C-star algebraic setting, but no. So it is an analog of freeness. And as long as you have, so for actions, classical actions of compact groups on compact spaces, as long as your orbit space has finite dimension, then freeness is the same as finiteness of the Rocking dimension. Okay, so this is very strong. But there are examples, like this example I already mentioned, when you have infinite product of Z2 acting on infinite product of S1, where this is free, but the Rocking dimension is infinite. Okay, so that's why the local triviality dimension is interesting. And now to the main part. So first of all, what are the difficulties? Now I want to go beyond compact. And most of the difficulties I'll be listing here are just about rephrasing in topological terms to get any grasp of how to actually generalize this. Okay, so this is what we're dealing with here. So first of all, I was talking a lot about partitions of unity, and they were in the C-star algebra, but in this case, they'll only be bounded. They're not compactly supported or vanishing at infinity, because if you look at this functions on a space that is not compact, and still you have this, they have to add up to 1, right? So this implies that they cannot have compact support or vanish at infinity. So your partition of unity functions, they will be only bounded. So they will be in the multipliers somehow. But so this is maybe not a big problem, but it's something you have to take into account. And then if you have a locally compact principal bundle, your trivializing cover is no longer finite, right? Because in the compact case, you always can find a finite subcover. Here, well, your trivializing covers may have infinite cardinality. So the questions of convergence appears. So of course, in the classical setting, when you have this sum for your principal bundle, you always assume that it's you only finitely many functions from your partition of unity are non-zero, so there's no question of convergence. But however, you have also those more general partitions of unity where you don't. So these will be called locally finite. But if you don't have a locally finite partition of unity, you only say like this sum pointwise converges or something like that. Then, well, there are some questions that you have to think about, and I'll give you just a flavor what kind of convergence we can look at for those function spaces that we will be dealing with. Then there's another thing with this unreduced cone. If you have a locally compact space, or a locally compact group, then this cone may not be locally compact. So there are no compact neighborhood of the tip of the cone. That's basically the proof. Of course, you have to write it down and very carefully, but that's basically the idea. So we cannot use Gelfand-Naimark duality. You have to look at some other dualities to generalize a bit this to the setting. And in the abstract, I talked about pro-C-star algebras and duality between some topological spaces and commutative unit of pro-C-star algebras. Here, when I was preparing this talk, I thought of something different. We'll see how it works out. Well, by the way, I should also say that this is really a work in progress. So this is the first time I'm talking about those results to anyone. So yes, so any comments or finding mistakes is welcome. Okay, I believe that even if we somehow avoid the unreduced cones, there's this universal principal G bundle EG, which will never be locally compact, right? You can, this Milner space that classify all numerable principal bundles. And I think that sooner or later, you'll have to work with non-compact spaces, and you have to find a way to do this. And I think the sooner the better. So that's why I want to do it from the very beginning. And the other difficulty is that there are actually not so many examples of free actions of locally compact groups on the non-Uniwersytet algebras. Well, not as many as for in the compact case. And this paper by David Elwood, when he generalizes everything to this crazy generality of locally compact quantum group actions on non-Uniwersytet algebras, his example is the U1 action on, I don't know, just, I think some Q-deformed spheres, right? So it would be better.
Even torus, maybe even.
Or even torus, okay. It would be better to have more examples so you can really build this theory, because if you only have some commutative examples, then you might miss some non-commutative effects that take place, right? So these are the difficulties. I'll try to overcome them. I might not be able to do to overcome the last one. I'll give you some examples, but maybe not that many. Okay, and now reformulation in locally compact case. So just for the sake of this talk, so you can do it in the most general case or the locally compact group, locally compact G space, but let me assume that G and X are second countable. And why? So second countability of X will imply paracompactness, okay? So locally compact second countable spaces are sigma compact, and then locally compact sigma compact spaces are paracompact. And then second countability for G, I will need this for metrizability. So then second countable locally compact groups are metrizable. And to give you the easiest possible, so that's my idea for now, the easiest possible overview of how to work with this, I'll assume this second countability. However, you can get rid of it, but this would require a longer talk. Okay, and now the interesting part comes. So on CG, on this unreduced cones, you can look at two topologies actually. So one topology is the quotient topology, okay, and that's the standard thing. And then you can look at the Milner topology, and I called Milner topology because he introduced it when he was talking about joins, okay, and those universal spaces. And the cone is a join of a space with a point, okay, and that's why this is the same actually. So this Milner topology is the initial topology with respect to the maps. First of all, this height map, and then you have some kind of an other coordinate map, right? But it's not defined on whole CG, but only at the preimage of this. But it turns out so this is only a partial map, but it's not a problem. You can still take preimages of open sets, and then this will give you a basis of your topology. Okay, so that's this. And to be honest with you, this slide, the things I'm talking about on this slide just took me months to realize. So first of all, the first thing I realized is that there was this subtlety of this theorem that I was just presenting to everyone without much thought, because in compact case, it should all work, right? So suppose you have a Stenoth principal G bundle, and then you have your partition of unity, you have your trivializing maps, and you compose out of them, you have this map. But this is a map into CG. If you consider quotient topology here, so quotient topology is good for saying where maps out of CG are continuous or not, right? This is what it's good for. But so we need some initial topology here to easily say whether those maps are continuous or not. And what is good is that in the compact setting, those two topologies are equivalent, and you can also find it in books. Okay, so that's good. So in the compact setting, the quotient topology and this Milner topology are the same. Okay, now the question.
Could you recall, please, what initial topology is?
So initial topology basically means that you have some maps like here, and the basis of your topology is pre-image of open subsets via those maps, right? So you take the smallest topology such that.
So this is continuous.
Yes.
Okay, thank you.
Right, and it's good to have a space that have both like a finite topology, which is quotient topology, and initial topology, right? So you have a topology with both finite and initial. So it's good to saying whether it maps out of that space or into that space. You can easily check whether they are continuous or not. Well, easily. You have at least some theorems to work with. And it turns out that in the locally compact case, this is also true. Okay, so the two topologies coincide, but this is far from trivial, at least for me, because here, what you actually prove is that, and it will work if G is not second countable as well. The only thing you need is that to know is that locally compact groups are automatically paracompact. Okay, so that's some theorem to prove, and then you have to know that this cone, this quotient map from 0, 0, 1 times G2, this cone, that this map is compact covering. So in this CG, all the compact subsets are basically just some images of this quotient map of compact subsets from, well, they're above via this quotient map. And this is actually, I think you can find some space, if your space is not paracompact, then you can find some examples where this does not work, and then these topologies would not coincide. Okay, so this is some subtlety, and this is a lot of general topology, and looking it up in some books or just finding it on your own. That's why I'm talking about this long time, because it took me a long time to realize. But it's all good. It's the two topologies coincide, and we can again write down the theorem in exactly the same way. So you just generalize the theorem with one exception. So first of all, you still have a lot of maps, but now you don't know if there's a finite amount of them, right? And that's why I'm assuming this second countability, right? So I know that my space is paracompact, so I can always find some partition of unity. And then the question of convergence of this sum, right? You can either talk, if you want to really mimic the partition of unity part, well, if you have a locally finite partition of unity, then this will converge locally uniformly, right? But this, in the locally compact case, is equivalent to compact convergence or compact open topology convergence. Okay, and I'm talking about this compact open topology because I have a way of generalizing this to the non-commutative setting. And in the classical case, it's equivalent. You could even talk, I think, about pointwise convergence, and everything should work. I would have to check this, but I think this is not the real issue. This is a bounded, this will always be some bounded sequence. And I think in that case, on bounded sequences, either you take locally uniformly, compactly, compact open, or pointwise. For the sake of this theorem, it should work. It's a bit subtle because if you start with a partition of unity, if you don't start with a partition of unity, but only with this, so you want to prove it that you have those maps, and you want to prove that you get the Stenoth principal one. Okay, you have some sum that converges locally uniformly or compactly. This implies pointwise convergence, but then you can prove that if you have some kind of a generalized partition of unity, you can always make an actual partition of unity out of it. Okay, so that's the main ingredient, like the main difficulty in this proof. Okay, are there any questions about this?
I have a question about assumptions.
Yeah, I had the same.
because we had already a discussion about the difference between between these partitions of unity and open coverings. And now we are using the compact open topology. Are you defining this compact open topology in terms of other partitions of unity? What's going on here?
So what I mean by compact open topology is just I take it on the set of all continuous functions on X, okay? Because these are just continuous functions from X to C. So then compact convergence is equivalent to compact open topology. That's what I meant. Yeah, sorry if I was not clear.
Okay. So the only open subsets are now in where? No.
In X. Actually, we're talking about this X is this principal bundle, right? X over X mod G. And I'm assuming that X is paracompact here. Okay, so
X is, yes. So therefore, I asked about subsets. X is paracompact. Yeah.
Yeah.
Yeah. And this is the assumption which is not easy to generalize to this non-commutative setting. You said.
Yes, but there's a different assumption. You just might. So I'm talking. So this is maybe a cheap way to do this because I'm trying to just assume paracompact so everything works. But then I can try to generalize maybe not paracompact principal bundles, but numerable ones. And this I can do. But for the sake of clarity, I'm assuming now everything I can, and then I'll have this comment at the end that everything will work in this more general setting. But yeah, but those are all good questions.
So okay, let's summarize the assumptions of this theorem. So I understand that everything which is up above applies, right?
Yes, yes, that's for all my slides. If something is above, it applies to the rest of the slide.
Okay, so all of this. So locally compact Hausdorff for X, locally compact Hausdorff G space, and X and G are second countable. And and then does it imply paracompactness for X or not?
Yes. Does. So that's exactly it. So that's why I said so. Locally compact second countable spaces are sigma compact, and then locally compact sigma compact spaces are paracompact. So if you want to just use some like references from books.
Okay, thank you. Yes.
Okay, great. So then we have this, but still, well, I have some generalization of the theorem, but what about generalizing it to topology? So the problem is that this C of G is not locally compact. And however, because I am assuming G is second countable, one can prove that it will be completely regular. And for the sake of my talk, this will be enough. So here, okay, so on this slide, there's some general result about completely regular spaces. You have Y a completely regular space, and C of Y, you take all continuous functions, complex value functions on Y. And I consider the compact open topology. So just topology, it's uniform convergence on compact subsets, basically, right? This is equivalent. And what do I have? I define the character space. So, okay, so I'm taking characters, so star homomorphisms, and I assume continuity with respect to this compact open topology. And then there's this, well, you can find this result in some old, really old papers. One by Michael and by Morris and Hubert, and that if you have a completely regular space, then this map, if we have our, well, good old Gauss-Van duality, this is how we prove this homeomorphism between Y and the character space of C of Y, right? That's the same way. And this is how, and we need complete regularity, actually. This is the generality of the theorem. If your space is completely regular, then this map will be a homeomorphism when here on this character space, we consider the weak star topology. And few words about the proof. So surjectivity and continuity of this map. To prove it, you don't need completely regular. This would work, I don't know at what generality, but you don't need complete regularity to this. But you need complete regularity to prove injectivity, because on a completely regular space, continuous functions separate points. And you need this to prove that it's a homeomorphism, that this map the other way around is actually continuous right? Because you have a bijection, continuous bijection, but to prove that the inverse is continuous, you need the following fact, that on a completely regular space, the topology is actually the topology which is initial with respect to all continuous functions. Okay? And that's what you use to prove that it's a homeomorphism. So this is some old results. And I find it really interesting that you can go this far, that something I knew for compact spaces, right? Which then the proof is goes more or less the same, but well, we have much more properties satisfied by compact spaces. But then for regular, completely regular spaces, it works as well. And this is crucial if you want to go like back and forth, like you have maps between spaces and then maps between algebras, and some exactly this theorem, right? If we now have two completely regular spaces, then either you have a continuous map between Y and Z, or you have a unitary star homomorphism, which is continuous with respect to the compact open topology. So when I talk about all continuous functions here, right? So on a space that it might not be compact.
Sorry, may I have a question?
Yes.
So regarding this remark about this initial topology, so correct me if I'm wrong. So you start with some topological space Y, then you consider the algebra of all continuous function on Y, and then you forget the original topology and define new topology, which is initial topology to this family of functions. Yes. And the result is that you would get the same topology, not the weaker one. Yes. Yes, for completely regular spaces. I see. Thank you. Quite interesting. I didn't know this result. This is in Michael's paper. This is really, and it's probably well known, right?
Spelling of Michael probably is.
Sorry, I have a suggestion. Like
Michael, the name of the name Michael.
Oh, wrong spelling. Yeah, thank you. Yeah, thank you. Alex, you had some suggestions.
So I have a suggestion. I mean, like, you know, like this compact open topology, like, so I think, I mean, like, so the way this was like built was like that, to have like a most generic, like kind of a junction between topological spaces. And so basically, like you're saying that completely regular spaces are the fixed points of your junction. So in a way, you have this junction, right? Like, so think about like, I'm not going to write it out like no or tell anything, but I mean, like, so you have a unit and a co-unit, and like, and you can ask then when is the unit an isomorphism, and it looks like that. Okay, for completely regular spaces, this is an isomorphism, so a homomorphism, and maybe you can also go the other way around. Like say which ones are exactly the.
Yes, that's true, because so I'm not saying that there's any duality here, right? I'm not saying that you have completely regular spaces and they correspond to some algebras. I don't know. I only have this result, which is enough to prove some equivalences and to prove a theorem, which I have probably here. Oh, okay. So I'm only saying this, right? That if I have a continuous map, then I have this, and I can go the other way around. Thanks to that theorem, that I know that the character space is exactly Y again, right? So that's this part. And you could do this in some more general way, but I wanted to do this in this way because it's really visible what we're doing here. And then if G is second countable, then C of G is completely regular, as I told you, and then the above result is applicable, and I can now have a reformulation of this local triviality in terms of continuous functions. Maybe not C star algebraically, because we could talk about all continuous functions, but there is a way to go around this.
So what will these function algebras be now? Pro-C star algebras? What will they become?
Yes, that's what I will say in a second. This will be the Pedersen of multipliers of the Pedersen ideal. This would be this is my idea to generalize this. Let me very quickly go. It's okay. And now this comment is to just emphasize, because Tomek noticed that actually what we want to do, what we are doing is just generalizing numerable principal bundles, not all. And here, if G is not second countable, then we can use this more general duality between, and here are some adjectives. I don't want to give you the precise definition, but some class of spaces, and then Untitled process algebras. Okay, and if you use this duality, then you get this kind of one-to-one correspondence.
And
however,
when you say completely Hausdorff spaces, you mean completely, right? No, what does it mean completely Hausdorff?
That I have so I think that for any points, I have a function that is one, this has one at one. Well, let me.
Yes, but this is probably a typo. You meant completely regular. Yes, not completely.
No, here I mean completely Hausdorff. There's the notion of completely Hausdorff spaces.
That's what I thought to begin with, but then I realized no, completely regular doesn't fit.
Yeah, completely regular will not fit. So completely Hausdorff spaces. Ooh, do I remember the definition? That's why I wanted to not to talk about it, because I just it's just something. But it's just something. It's a separation axiom, but surely somehow it's stronger than Hausdorff. Yes. But it's not that it's implied by complete irregularity, for example. So it's a strange one. So regular or completely regular would not imply completely Hausdorff. So it's implies Hausdorffness, but it's. So it's stronger than Hausdorff, but it's not related to other separation axioms.
Okay, but just to be sure, this condition implies the existence of continuous function, yes?
Yes.
Okay.
So, and then there's this distinguished family of compact subsets. So you have some family that generates the topology and satisfies some results, some properties. But this is not that important, because this is just a remark that you can do it for non-second countable groups as well. But then what you are generalizing are not principal bundles, like all principal bundles, but only numerable ones. And this is exactly what I want to do, because only numerable principal bundles can be generalized. It can be, well, not generalized, can be classified. So you need to have this partition of unity. And for numerable principal bundle means that for at least one trivializing cover, you have a partition of unity. So this somehow generalizes paracompactness. And many things still work. And I think it was Albert Dold who introduced this numerability, and he proved a lot of results about this. Okay, let me maybe go.
Can I have a question about theorem that appeared?
Yeah, sure.
Maybe I'm missing something, but isn't it kind of trivial, this, say, first condition? Doesn't there always exist a continuous map?
Yes. Some things in this theorem are trivial, right? I called it theorem because it's not mine, so I don't want to insult anyone, right? So it's some of things are here very easy and trivial, right? If you have a continuous map like this, then this one will be always, you will always get this intra-star homomorphism, which is continuous.
I'm not saying that the implication is trivial, but I'm saying that the first bullet point always is true. Like you have always constant map of something like this. So maybe I am missing something.
But so I wanted to say that there's one-to-one correspondence. That's probably should be the statement. Yeah.
Oh, okay. That every interstar homomorphism arises as the composition.
Yeah,
okay, okay. That makes more sense.
That makes a lot of more sense. What I was thinking,
Yeah, okay. that makes a difference. Thank you, Jacek. Great. By the way, we have, Mariusz, you have an answer. Completely Hausdorff means that points can be separated by continuous functions.
Yeah, that's what I thought, but I couldn't phrase it somehow, and I thought that maybe I'll make a fool of myself. Okay, thank you very much. So that was someone in the chat, right?
Yes.
Yeah. Okay, thanks. That's it. Okay, so now reformulation, we can complete this. So with all the assumptions that I had above, just locally compact group, locally compact G space, both second countable, then I consider on both those function spaces, the compact open topology. What I get in the end is reformulation, but now I only use function spaces, right? So that's good. So I have J-covariant unital continuous star homomorphisms like this, and now this sum converges into compact open topology, right? And this is what I wanted to have, okay? And then the only question is that here I'm talking about all continuous functions and not just about functions vanishing at infinity. So how do I do this for C-star algebras? And so that's the actual question, right? I wrote it down here. What is the analog of C of X in the non-commutative topology for a locally compact X? And that's in the title of the slide. So these are the multipliers of the Pedersen ideal. That's what I think can help us here. So let me introduce this Pedersen ideal and then the multipliers. And I'll be quick here because I have like 5 minutes. So sorry for that, because that's the most technical part, but I'll be a bit quick here. So this is a standard definition that I take. First, I define this space K0 plus. So I take all positive elements in A for which there exists another positive element, such that for all functions phi, which are continuous on the spectrum of A and satisfy this condition, we have this. And you can write it down in many ways what this K0 plus is. I believe that this is the nicest way, and it has a lot of words in it, right? So that's easy to comprehend. And then you define this K plus, which is somehow like an order ideal generated by this K0 plus, or you can just read what I have written here. So you take only those for which there exists some AI such that this sum is bigger here than this, okay? And this is all going on in a C-star algebra, so this has a precise meaning, right? This comparison sign. Okay, if you have a K plus, then your definition of the Pedersen ideal is exactly, you take the span of all the elements here in the K plus. And this will be an A, and that's a paper from 1966, also a very old paper by Pedersen, where he proved that he wanted to do a measure theory for C-star algebras. So he wanted to have, for a general non-commutative C-star algebra, some analog of compactly supported functions. And what he defines here is this ideal, which then he proves so this is a two-sided, this is dense and order-related ideal in A, and that it's minimal among all such ideals. Okay? And that's really important if you want to prove any things regarding K of A. This minimality is usually coming in handy. Okay, and now the multipliers. This is
sorry, Mariusz, could you go back to the previous slide?
Sure.
I'm wondering about this condition here. So what do you mean by a function on the spectrum? You mean the values that the range is between 0 and 1?
Yes.
Okay, thank you.
Yeah. So here I'm of course using the functional calculus, right? Yeah, but this is what I mean, that the values are here. And so if you want to prove that in the commutative case, this is exactly, these are the compactly supported functions. This is an exercise to do to somehow understand this Pedersen ideal. And then this you can use this minimality, which would mean that the only thing you need to prove is that any compactly supported function is in here. Right? So it can be written down as a span of those Ks, where those Ks are defined like this. Right? So, and that's of course, it's not, maybe it is immediate for someone, but not for me. And I don't want to go into this because it's not needed for what is needed is that there exists such an ideal, and it gives you something which corresponds to the compactly supported functions. And then you can look at multipliers of this ideal. And here multipliers, I mean, like in the usual sense, like those double centralizers, right? You can also do this for a C-star algebra, but then you will get multipliers again because C-star algebra is a normed algebra, and then those multipliers are automatically bounded. But so now imagine that you look at those double centralizers of K of A, right? And then you will have some unbounded multipliers. You look at functions from Ka to Ka, and you only assume this condition. And from this condition, you can prove that they are linear and also that they are multipliers. So there's of course a lot to be done. I should have probably assumed linearity not to deal with any questions like it. But this is sufficient assumption to get everything that you want, that these are linear maps and that they are, well, left and right multipliers, S and T. And then the set of all multipliers is denoted like this. And then one can show that the Unitary star algebra, that this is a Unitary star algebra, and this is thanks to the fact that Ka is a Unitary, is not a Unitary but a star algebra. So the star comes from Ka. This is how it enables us to define the star operation here. The unit is, of course, you have this multiplier of just identity. Take identity and identity. And then you can also prove that the bounded multipliers, which would be the same as M of A, are here. And then there is an interesting topology that was defined by Lazar and Taylor on this algebra, on this Unitary algebra. And the topology is defined by the seminorms given here. So for any K, you have two seminorms defined as follows. Okay, and this topology that is given by this these seminorms is called the kappa topology. And now the most interesting part for us is that if A is commutative, so this is for some locally compact space X, A equals to C0 of X, then this ideal is exactly what I told you before, that this is the ideal of compactly supported functions, and then gamma of K of A equals C0, C of X is exactly, you take all the functions on X, and the kappa topology agrees with the compact open topology. Okay, so that's, they coincide. So that's the missing ingredient in this generalization, right? And this is also not immediate to prove this, right? That this is exactly equal, and then that this, that the topologies coincide, this is not that hard. But to prove that it's equal, that's why it's called a theorem. Okay, but it was known for some time. It was before Lazar and Taylor. This equality was known. Okay, and then now I can finally define this locally trivial GC star algebra, or maybe numerable locally trivial GC star algebra. That would be maybe a better name. So, okay, so the name is, I'm not sure if this will stay, but for now, I'm just copying some names from topology, that if you have a trivial space, then it has a equivalent map from X to G. If it's locally trivial, it has a covering by trivial algebra. So this is basically what I'm doing here. Now I assume that G is a locally compact group and A is a GC star algebra. And here again, I consider this compact open topology. And here I consider the kappa topology. And my definition is that, well, I do just the things that I had in my theorem, that there exist G-equivalent unitary star homomorphisms like this, and that I have this convergence in the kappa topology. Okay, so this is really a generalization. So first of all, so there are a few things to check. So first of all, this is a generalization of the classical setting, that's for sure, but it's also a generalization of the local triviality dimension. This is important to notice. So not only I have all the examples from the classical theory, but also I have all the examples from the compact quantum principal bundles case, but locally trivial ones. Okay, let me maybe a few comments how this goes, how this works. If now I'm in this commutative setting, then I have this, that A is locally trivial as a GC star algebra if and only if this is a Stenoth principal bundle. And this is really what I was going through, that my whole talk was about this. And it since I have this result and the kappa topology coincides with compact open topology, this really follows from our reformulation of the Stenoth principal bundles. Okay? And this is one result. I'm probably over time now, right?
Yeah, but finish. This is now getting very interesting.
Yes. Well, yeah. So, but this part, I think maybe it's more or less clear because I was talking about this a lot, right? How to generalize this, and of course, this is just one. This is just my proposal that this might be it. Of course, time will tell if this. So for starters, I have this one verification, right? That the classical case agrees, but this is not saying much really, because you can have a very trivial non-commutative generalization of some commutating things, right? However, there is something into it because this local triviality dimension is also generalized.
Yeah, this is very nice. But I'm still confused about your assumption. In this theorem here,
Yes.
No, the theorem, the next one.
Yes.
That you still have these assumptions that we had before, that this is second countable and so on.
Oh, thank you. Yeah. So here I should write down numerable Stenoth principal bundle.
Okay.
Yeah. Thank you very much. Yeah, this is what I'm generalizing.
Okay.
Yeah.
Perfect.
So that's a mistake.
Okay.
So you can either have this assumption of, let's say, you could say that A is sigma unital. So you have a countable approximate unit.
Yeah.
Then the space that it defines is locally compact and sigma compact, so it's Pareto.
Yeah.
But you're right. That was a good catch. That basically this is a numerable missing here.
Yeah. Because this time it's not in the assumptions above.
Yes. So I'm really sorry. I was really trying to be consistent with my assumptions, but it turned out in the end I just had so many different ideas. And let me tell you that if I would try to show you this in this most general setting, I would have to go through the theory of pro-C-star algebras and this very different, strange class of completely Hausdorff spaces with distinguished families of compact subsets. I think it would be much worse than what we did here. So however, it led to some confusion. So now I don't know if that was the right call, but okay. Let me just tell you about this local triviality dimension. If A has a unit, well, there's a typo here. So if A has a unit, yeah, thank you. Or if A is unital, yeah, then this multiplier algebra is again A, and the kappa topology coincides with the norm topology. So this is something which also happens for the multiplier algebra, right? That's when A is unital, then multiplier algebra is equal to A, and then the strict topology coincides with the norm topology. So this is the same old story. Here, if G is compact, then this is then this is unital. That's why. So this is a slide I prepared just before this talk, and it shows that first of all, A has a unit, and here I want to say that if G is compact, then C of G is unital, right? And of course, the compact open topology coincides with the norm topology. What I wanted to say is that if you look at the definition of the local triviality dimension, then we had the maps from C of G to A, which were in unital G equivariant star homomorphisms. So there was no talking about compact open topology or kappa topology. So that's why I'm trying to say that these actually coincides with norm topologies. And you get the same things. Okay, so if this dimension is finite, then A is local trivial as a GC star algebra. So it satisfies this definition that I have here. Okay, so this is very good because I still have those examples that I was talking about for the local triviality dimension. There's an interesting question, and I don't know how to answer it. Can we prove that for unital locally trivial GC star algebras, the family of star homomorphism has to be finite? So you start with something locally trivial GC star algebra. You have countably many of those maps, and can you prove that it has to be a finite number, like the finite subcover for a compact space, right? I don't know how to do this, how this should work. I had some ideas how to work with this, but this would really need pro-sister algebras and universal kind of spaces, things like that. But I don't have any precise arguments. Okay, but so that's interesting. And then I just wanted to talk about triviality. And so the message from this slide is just that if you have triviality in this new sense, so we have a homomorphism like this, right? This will imply triviality in this sense from like first slides of my talk. But there's implication one way only. And I think there's some kind of a quantum effect that you cannot have these two things to be equivalent. They will be equivalent in the commutative case and also when the primitive spectrum of A is compact. Because then the multipliers of the Pedersen ideal are the same as the usual multipliers. There's this result of, I think it was Lazar and Taylor who already proved this, or someone else, or maybe Phillips, that if the primitive spectrum of A is compact, then actually those multipliers are the usual multipliers of your algebra A. And then you have equivalence. But for some, I don't have a counterexample, but I also don't, I think it might, there's no reason for this to be equivalent for me, at least. So there's some equivalence here.
Can I ask a question? The last question. Yeah. What would be this, the last property? How would it like in the terms of checksum compactification, classically?
Which one? Which property?
You said
that the spectrum is compact.
No, this rephrasing by Lazar and.
So it's on this slide or somewhere else?
No. You are talking about the equivalence between multipliers and Pedersen multipliers in the case of compact primitive spectrum space.
But I think in the classical
classically it's compactness simply.
Yeah, that's true.
Yeah. Okay, so it's a subtlety only in the non-commutative realm.
Yeah, that's true. That's true. So yeah,
okay,
thank you for that.
Thank you.
Comment. So okay, so triviality is a bit tricky, but we have the implication the right way, right? So the triviality with my definition implies the triviality which we defined before. And for a lot of sister algebras, you have the implication both ways. Okay, and in the commutative setting, you don't see this. So if you go through the proof, I have a proof in the commutative setting, and really it's you use it heavily. You use this commutativity heavily, and then you don't see that there's a difference. But then you go non-commutative, and suddenly there might be a difference. I don't know yet. I don't have a counterexample of something that is, let's say, trivial in this sense, but it's not trivial in this sense. Okay, and let me finish with this. Also, I wanted just to say that I also have those examples that what Piotr mentioned, that if you only have this classical core, so you have your non-triviality is only classical, so you have a C0X algebra, but your X is coming from a principal bundle. Okay, so this is a very nice, so this is some kind of a definition that would also generalize local triviality, but it's, as Piotr said, it's somehow for non-commutative geometry, it's a bit disappointing because everything that is non-trivial in this principal bundle is happening in this classical core. It's happening in the center. So you don't, and the rest is just some like non-commutative background. However, there are still a lot of nice examples, like if G is torsion-free, this is exactly the same as the proper algebras of Gentner, Hickson, and Trout, where this proper action is in the sense of Baum-Cohn and Hickson. So there's a lot of interesting examples, and they are covered by my definition. First, you have to prove this lemma, and then you can show that those examples that are like only the non-triviality is only in the classical, at the classical level, they're also covered by my definition. Okay, and I went through this very fast because I don't want to talk about this more unless someone asks. So yeah, thank you for your attention. And there's some outlook. Okay, well, I want to find more examples, that's for sure. And this part, this is interesting to prove freeness in the sense of Elwood. I have a proof, but it's not complete. So that's why I didn't want to talk about this. I wanted to talk about only this reformulation. And then there are some other things that one can do, including going to locally compact quantum groups, right? Everything should work well, but of course, this is much more subtle. So, okay, so now thank you for your attention.
Yeah, thank you so much, Mariusz. Now, so when you say you have a proof, it just means that your margin is not large enough to write it down, right?
Yeah, so I have an idea of the proof. That's what I should say.
Okay, let's start with questions. Stefan, go ahead, please.
Hey, Mariusz. Can you hear me?
Yeah, we can hear you.
Hi, okay, perfect. First of all, thanks for the very nice and interesting talk. I have two questions, if I may. You were talking about clefness a bit earlier, but then I was a bit busy with the newborn. Can you say, were you able to compute the local triviality dimension for cleft bundles?
So actually what I was talking about clefness is that we with Piotr were trying to ask you about the definition, because we know that you have something in your papers and I don't know much about this. And I don't know, so that would be interesting because of course, so this clefness should be implied by triviality, right?
Yeah, I mean, absolutely, it's free. I mean, yeah, cleft bundles are free, so I guess yes.
Yeah, but clefness is of course implied by triviality, but the thing is, it's not implied the other way around. So Stefan's question is absolutely valid. You have a cleft principal bundle, and what is its local triviality dimension? You can easily, with Ludwig, we have some example that, I don't know, the number is equal to 2 or something, or 1. Okay. So that's in the classical case. But in general, this is an interesting question. But maybe since this cleftness came up, let me say that I remember ages ago I had lengthy discussions with Nigel Hickson because I was bothering him. Look, we have this idea of cross products and everything works so beautifully and it's fundamental. And this is a right generalization for triviality of principal bundles. But in Hofgalois theory, the concept of cleftness is omnipresent because these are so-called cocycle cross products, okay? And how do we do it? How do I make sense out of a convolution invertible map at the level of C-star algebra? And then Nigel was convincing me, no way, Jose, there is no way to do it. And then we bumped into your paper with Mariusz, and it seems that you somehow figured it out. But I must admit, I haven't read it yet.
Yeah. I mean, that sounds very interesting. I mean, we were just studying. We were studying this on different levels, and then the definition that we use is, whenever you have a compact group, actually you have this nice representation theory, and so you get this isotypic components, and then our definition is that the isotypic components contain invertible elements, and well, this actually also helps you to have all this. I mean, to get the classification in terms of cocycles and all these kinds of things. So I mean, it would be just interesting if it's like really, I mean, maybe it's just 0 or maybe something else. I don't know. So yeah, maybe this is something one could look into. And and Mariusz, if I may ask another question, I mean, which is related, because I was already saying a classification. So so in this context of locally trivial principal bundles. Have you thought about a classification theory? So can you, I mean, classify them in terms of, I don't know, you really take the fixed point algebra and you group, and then can you classify all those which are locally trivial?
So first question is as follows. So if you have an equivariant star homomorphism between unital C-star algebras that have isomorphic fixed point subalgebra, right? Is that automatically an isomorphism? Because that's the true in the classical setting, that equivariant maps between bundles over the same base space is a homeomorphism. And even what we were doing is that if you have a map from G to G, which is equivariant, it turns out to be a homeomorphism. That's something that is classically true. And then Alex Kirvasity was able to prove it for any for compact quantum groups. So if you have a collinear map, like G collinear map from C of G to C of G for a compact quantum group, then it is an isomorphism. So that's telling you that we're going in a good direction, but then we don't know, and I would love to see, I know the proof in the Hopf-Galois setting, that if I have a collinear map between A and B and they have the same fixed point subalgebra, then this is an isomorphism. So algebraically, it's true. So for some completions like universal one, it would be also true. So that would be a way of, because in the usual classification of bundles, you have those classes, right? Because if you have any map between them, then they are in the same class. And then you define classification in, well, you look at bijection between those classes and maps into the classifying space, like homotopy classes of maps. And this we can try to do in this setting, in this local trivial setting. However, this will go, I wrote down in those difficulties. To have a classification, what you have to have is this EG space of Milner, this thing here. And this EG space, you cannot talk about it in terms of just the Pedersen multipliers or stuff like that. So if you want to do it for, let's say, quantum groups, then I don't know what EG is. I have some ideas, but it will be a pro-C-star algebra, probably, but how to use it to do any classification. This is actually something I'm working on in my project. I'm trying to understand how to classify these principal bundles, but I don't have any answers. I only have those ideas that I told you. Yeah, but that's really interesting to me. So yeah.
Okay. Yeah. Thank you so much. Yes.
Thanks a lot.
Thank you. Adam, go ahead.
Yeah, so I have a very simple question. If we start with A equal to be the algebra of compact operators, so what is the Pedersen ideal? Is the ideal of finite rank?
Yes. Yes.
Okay, thanks. That was quick.
And then the multiplier algebra of this idea would again be B of H.
Yes, yes, that's what I expect.
Yeah.
Thanks.
So Mariusz, maybe you can show again this, because I want to somehow summarize your talk to have this take-home message. So if you could show your definition first of what you mean by local triviality in this more general setting.
Yeah, this is it.
Yes, that's it. This is a crucial definition. So you use this Pedersen's multipliers here, I understand, okay. And G is still classical, but is locally compact, okay. Yes. And A is, what is important, A is not unital. Okay, and if it's unital, you showed how you recover the compact case, but not completely. I understand that you recover this compact case only for classical groups acting on unital sister algebra.
Yes,
right?
yes,
okay.
You're right.
But that's already a lot. And okay, so this I understand. And you have this convergence. It's one of the things which I think is worth emphasizing, and perhaps you did it, but let's do it again. The non-compact case is difficult because you no longer have this finiteness. I mean, when you are compact, you simply have that every open cover has a finite subcover. So no matter how huge is your cover that's locally trivializing your bundle by assumption, you can always choose a finite one. So you might as well from the start put this finiteness condition. And this is of course no longer the case. You can easily have locally trivial principal bundles that have local triviality dimension as we defined it, infinite, right? So that's finiteness implying local triviality. It really strictly works only in the compact case for trivial reasons. Okay, so this is good. And the main result again, please.
Well, which would be the main result? Is that one or this one?
Okay, if it is finite, then A is locally trivial.
So I have just two like main results. So of course, one is that this is a good generalization, right? So I have this, and the other one is that it's also generalizing this case of this local triviality dimension. And as you said, in the non-compact case, this local triviality dimension is no longer a good invariant, right? Because it's
yeah, exactly. So can you go back to this theorem one more time?
Yep.
So A is locally trivial as a GC star algebra if and only yes. So first is the commutative case. This is recovering the commutative case in case of numerable Stenoth principal bundles. Yes. Okay. Okay. I'm completely happy. Any other questions?
Can I comment on this?
Yeah, sure.
So your two main theorems could be rephrased as this. So you have a definition of a numerable Stenoth principal bundle with a, even in the non-commutative setting. And then you can speak about finite numerable Stenoth dimension, let's say.
Yes.
So that's the meaning. You can generalize this notion of the numeral Stenoth principal bundle. Yeah. So forgetting about local triviality, which is misleading.
Yeah, in a sense.
Yeah. Okay. So that's the point for me.
Yes, that's exactly the point, and that's so. This is a talk where I try to generalize something, right? So I know how there are no like really hard theorems, but to come up with the generalization, I think it's. I showed you just as we were going step by step that this is really not trivial. And I was doing this for a few months now, and I'm only now getting this answer that I believe is okay, and an answer that will prove this Elwood freeness condition. Because
but why is local triviality misleading? It's local triviality for numerable Stenoth principal G bundles. Why is it misleading?
Yeah, but if you use Stenoth, then this is
local triviality is for free.
Yes. I'm so sorry. Yes. Yes, of course. Yes. Stenoth has local triviality inside, of course.
So for a second, I thought of calling those algebras Stenoth GC star algebras, but this would be too much probably.
Yeah.
Okay, now I've got it. I'm so sorry. Of course, guys, you're right. Local triviality of Stenoth, that's confusing. You're right.
But numerable Stenoth dimension sounds sexy. Okay. I have another question. Do you have a source for this result about Hopf-Galois extensions that every G-equivariant homomorphism covering the identity on the base is an isomorphism?
I think it's in the original Schneider paper, and I can point you to the proposition, but I will have to look it up. But I think it's there because I was looking at this as well because I think it's a really interesting problem, right? And then the question of proving it for C-star algebras. So for any completion, because so if you have it at the Hopf-Galois level, then you have it for one completion at least, but then you would like to have it for all. And then I don't know. I was looking at the proof of Alex because he proved that when A and B are C of G, right? Then that this is true, that this collinear map is an isomorphism, or G equivariant map is an isomorphism at the level of C-star algebras. But his proof is really conceptual, and he's really using the power of the theory of representations of compact quantum groups and the fact that everything is really algebraic. And when you have this Peter Weil algebra, it's not entirely algebraic, right? There's some analysis part of it that you cannot just write down some finite combination and try to do computations and stuff like that. But I think it's in the Schneider's paper in the original one, this result.
Great.
Okay, thank you. Very good.
Okay, we are way over time, so maybe it's time to thank our speaker again. Thank you, Mariusz, very much for a very interesting talk.
Thank you.
Of course, I'm biased because that's my cup of tea, but I think you've done a very good job. And what I particularly like about this exposition is that it shows its attachment to different parts of mathematics. And I think it's very precious. It reaches out in many directions, and this is what I enjoy very much here. Okay, I stop recording right now.